Hello, welcome to the video presentation of Dynamic Eigenmodes Part 2, Applications. My name is John T. Kim. If you are watching our presentations for the first time, I recommend that you check Part 1, which is listed on the link below. Before we embark on the second part of the series, I would like to briefly summarize what we covered in Part 1. We are interested in how to efficiently calculate a parametrically rich vector space of a dynamic system undergoing parameter variations. By this, we mean that we want to find out and get a multidimensional vector space of a minimum possible size that will span all the solutions of the system when the parameters change from one combination to another. To this end, we broke the solution, system matrices, as well as the parameters into two parts, the nominal and the perturbed part. Then we obtained two new equations, namely the nominal and perturbed equations, by inserting the expressions x is equal to x naught plus delta x, mu is equal to mu naught plus delta mu into the original equation. By considering the transfer function from x naught to delta x and decomposing it into dynamic eigenvalues and dynamic eigenmodes, we concluded that the original perturbed system and the so-called modally equivalent perturbed system, MAPS, share the same solution space. That is, the dynamic eigenmodes of the MAPS do not change with respect to the parameters. Since the MAPS has the perturbed matrix delta A appearing only in each forcing term, it is essentially an ordinary differential equation with time-varying forcing input. It is this advantage that makes it extremely convenient to solve the MAPS instead of the original perturbed system. The total vector space that we are seeking for would be the sum of phi 0, the modes from the nominal solution, and phi 1, the modes from the MAPS. A few words on part 1. First, as opposed to the traditional static eigenmodes, which are basically the solution of Ax is equal to lambda x, the dynamic eigenmodes vary with time or frequency and are calculated by considering the transfer function matrix from the nominal solution to the perturbed solution. The word perturbed is somewhat misleading here because there is actually no limitation on the magnitude of the perturbation that we cannot take. Normally, a perturbation would mean a small deviation from the reference point, but that is not what's implied in the formulation of the dynamic eigenmodes. Secondly, I want to stress that unlike the static eigenmodes, which are used to express the system response by the conventional linear superposition, the dynamic eigenmodes are used through time convolutions between the dynamic eigenmodes and the generalized coordinates. As you can see in this expression, the perturbed solution is obtained by triple time convolutions. Third, some of the viewers might be concerned that using dynamic eigenmodes in the time convolution would be very inconvenient, not to mention that it is computationally expensive. This worry is well justified. However, there is an alternative. Since we are only seeking for the parametrically rich vector space, if not the solutions themselves, the task can be done not necessarily using the dynamic eigenmodes, but other modes in the normal vector space, as long as they both share the same space. These modes, not varying in time or frequency, but fixed, are obtained as follows. Sample the perturbed solution delta x prime using the maps at given frequencies, and process them by singular value decomposition to get modes set phi 1. Similarly, phi naught is obtained by singular value decomposition of frequency samples of the nominal system. The total set of modes phi is obtained by collecting phi naught and phi 1. With the exception of Flutter prediction, which we will discuss in the next and final episode, this is how we will calculate the parametrically rich vector space. Next, Shashank will present the rest of the Part 2 presentation.
In the previous video, we saw the mass spring damper example where parameter variation was introduced to a single element of the system matrix. However, in general, parameters may be spread throughout the system and vary continuously within the given range. We find, however, that it is not necessary to integrate over the entire range of parameters. If we randomly select mu sub i's, we find the rank of the perturbed matrix delta A phi sub 0 converges by about the sixth mu sub I. This is because although there are an infinite number of ways the parameters can combine, there are only so many dimensions that can be affected by the parameter variation, with the number being equal to the system dimension n. Regardless of parameter variation, they can affect at most n degrees of freedom. A new HOMEPS equation subject to a finite sum of randomly selected discrete perturbed matrices may account for continuous parameter variation. Notice that to guarantee the dynamic independence of the multiple inputs, replace the nominal solution x sub 0 by phi sub 0 r naught I, where phi sub 0 is the mode set from the nominal solution and r naught sub i's are statistically uncorrelated time signals. The modes of the perturbed system are guaranteed to converge as more discrete matrices are added. Typically, that number is less than 10, as we saw in the plot in the last slide. Naturally, a first application of dynamic eigenmodes would be to construct reduced order models. With the modes obtained, we may account for whole ranges of parameters specified, in contrast with a static eigenmode reduced order model. This can be done conveniently with the mode set phi with the Galerkin projection method, where we are transforming the system matrices into the modal coordinates. In other words, we are minimizing the error associated with using the subdimensional modes by making sure the error vector is perpendicular to the subspace spanned by the modes. To see the dynamic eigen decomposition in action for a parametrically rich reduced order model, consider an example from Aero Elasticity, the study of interactions between structure and aerodynamics, important to designing, analyzing, and testing aircraft structures. The Goland wing we modeled using a finite element and coupled with the unsteady vortex lattice, aerodynamics for aeroelastic simulations. For parameter variations, we consider 5 parameters in 1/4 of the wing as shown in red. These 5 parameters are the material density, Young's modulus, Poisson ratio, air density, and air speed. The nominal values of the parameters, mu0, and the range of variations are listed in Table 1. Table 2 shows 8 discrete variations that we used in mode calculations and also simulated for validation of the reduced models. In the plot on the left, we have rank of the perturbation input versus the number of discrete variations, showing that including 4 of them is sufficient for the rank to converge. The plot on the right shows the maximum errors in the time histories when simulated based on the reduced order models and tested for the 8 different cases. It can be shown that indeed including 4 discrete matrices generates the minimum errors. Surprisingly, including just one of them results in sufficiently small errors. The parametric reduced order model, or PROM, we constructed has the size 171 by 171, where the original aeroelastic model was 1012 by 1012. The top 2 plots are eigenvalues for the case of mu sub 4, at the velocity 150 feet per second, and air density rho 3.5654 times 10 to the minus 3, There is an excellent match between the eigenvalues of the full order model and the eigenvalues of the parametric reduced order model. The bottom plots are time histories of the vertical deflection and angle at the wingtip given an initial condition. Again, there are excellent matches between full order model and parametric reduced order model. When the same parametric reduced order model is tested for mu sub 8, which represents the most severe variation from the nominal values of the 8, again we get outstanding matches in both the aeroelastic eigenvalues and time histories, proving the validity of the parametric reduced order model. Next, we use the 171 by 171 parametric reduced order model in Flutter optimization. Flutter is a life-threatening situation concerning the flight safety and structural integrity of every airplane. It refers to a dynamic instability, which the interaction between the flexible structure and unsteady aerodynamics is such that any small disturbance will lead to gradual and sustaining oscillation of the wing. At any airspeed slightly higher than the flutter speed, the wing will diverge and be broken catastrophically. Therefore, airplanes must be designed such that no flutter occurs within the operating flight range. The goal of the optimization was to maximize the flutter speed of the Golan wing by optimizing the values of the 4 remaining parameters, i.e. Young's modulus, Poisson's ratio, material mass, and air density. The table shows that using the full order model, it took 18 hours and 51 minutes of CPU time to finish the optimization, whereas using the parametric reduced order model took only 4 hours and 27 minutes of CPU time. Thus, the parametric reduced order model could reduce the time by a factor of 4. In theory, a MEP solution delta x prime and the original perturbed solution delta x share the same vector space SR. However, it becomes difficult to capture SR if the rank of delta A is too large. If the parameters permeate through too large a portion of the system, for instance in a compressible airflow, Mach number plays a big role, affecting the entire domain of the flow, and it is in these situations where the first order MEPs may not be enough to produce the modally rich vector space. One remedy is to expand the MEPs beyond first order to the mth order as follows. Again, delta xm prime does not equal delta x, but it shares the same solution space as delta x, with a richer modal content than the first order MEPs. Hence, it can account for a large domain of the parameter changes or the high rank of delta A, when a sufficient number of higher order terms are included. If we use the matrix Neumann series to expand j omega I minus a naught minus delta A inverse around a naught and write out for delta x of omega, we get the same expression as the higher order MEPs. However, the interpretation of the Neumann series is entirely different than the interpretation of the higher order MEPs. While the Neumann series may or may not converge depending on the matrix norm j omega I minus a naught inverse delta A, the higher order MEPs always converges in its approximation of the modal space of the matrix function. The following diagrams show graphically this fundamental difference between the higher order MEPs and the matrix Neumann series. On the left, we have a situation where the Neumann series converges to an approximation of the true vector x as higher terms are added. On the right, we see the approximation gets off more and more as higher terms are added, diverging from x. However, in both cases, the higher order MEPs converges. That is, the true vector space of x is captured more accurately as more of the higher order terms are added in the higher order MEPs, although as an approximation of x, it may or may not converge. For an application of the higher order MEPs, consider the 2D airfoil undergoing plunging and pitching motions in the subsonic flow. we used an Euler CFD solver to model and simulate unsteady oscillations of the wing in the compressible flow. The picture shows the computational grids used in the modeling. As discussed earlier, the entire domain of the flow is affected by Mach number, which is a measure of compressibility of the air. Therefore, we are dealing with a global parameter variation that affects the entire flow domain. We can expect the first-order MEPS will not generate a vector space that is modally rich. We need the higher-order MEPS towards that end. The size of the full-order model is 5,776 by 5,776, and Mach number is varied between the range 0.3 to 0.5. We built 3 different parametric reduced order models, with the first 2 being the first-order MEPS, and the last is the second-order MEPS. With Mach number affecting the entire domain, the rank of the perturbation input versus number of discrete matrices shows little sign of convergence. However, checking the singular values against the number reveals that they hardly change even when only 2 discrete delta A's are included. For these reasons, we include 2 discrete matrices for the prom 3. This plot shows eigenvalues of the various orders for Mach equals 0.325. These eigenvalues were obtained by solving the eigenvalue problem AV equals lambda v. It is seen that all 4 models, including the full-order model, have their eigenvalues in the left half of the complex plane, meaning that the unsteady flow field is stable. Indeed, it is expected that the dynamically linearized flow is stable. The flow will not diverge due to any slight disturbances. Note that the sizes of the parametric reduced order models are relatively large compared to the size of the full order model. This is because, as said earlier, in compressible flows, Mach number plays a very important role affecting the entire flow, particularly in transonic zones. This is in contrast to our Golan wing model, where we only had a localized parameter variation. Instead here, we have a global effect from the Mach number. In the perspective of gauge modal invariance, which will be expanded on in part 3 of the video series, the proms are relatively large to capture richer gauge symmetries in the flow field. These plots are frequency responses of the 2x2 generalized aerodynamic force elements Qij. For example, Q12 is the aerodynamic force in the vertical direction due to the pitching. Q21 is the aerodynamic force in the rotational degree of freedom or moment due to the plunging. There are very good matches between the full order model and all 3 parametric reduced order models. When the Mach is increased to 0.425, however, parametric reduced order model 1, which is based on the first order MEPS, cannot hold stable, as a few of its eigenvalues become unstable. Apart from prom 1, prom 2 and 3 are stable, and their frequency responses show excellent agreement with the full order model. This concludes part 2. In part 3, we can look forward to Flutter prediction using the dynamic eigen decomposition and a frequency domain stability analysis, applications to linear time-varying systems, applications to nonlinear systems, and gauge modal invariance. So be on the lookout for part 3, or read the papers in the descriptions to get ahead. Thank you for watching. Please like the video, leave a comment with any questions, share, and subscribe to the channel for more dynamic eigen decomposition, theory, and applications.